Fuel system requirements. The engine's fuel system is a crucial component that needs to reliably supply fuel to the engine's fuel metering device, regardless of the ground or air conditions. It has to adapt to various altitudes and climates seamlessly. Two of the most common fuels used are avgas for reciprocating engines and Jet A for turbine engines. Avgas typically comes in two flavors, 80, marked red, or 100 LL, marked blue, where LL stands for low lead, despite containing 4 times the lead of 80-octane avgas. Jet A, on the other hand, is a kerosene-based fuel that looks clear to straw in color. The introduction of electronic engine controls has been a game-changer. These controls offer precise regulation of fuel flow to the engine, ensuring an accurate mix of fuel and air. For gas turbines, fuel controls have significantly advanced, effectively managing fuel across all flight conditions. Electronics and digital computing have facilitated seamless integration between aircraft and engines. By utilizing electronic sensors and computer logic within controls, engines can be managed with heightened precision. Factors like fuel cost and availability have also influenced the development of efficient and accurate fuel systems. Many engines now employ an interactive system where sensors relay engine data to an onboard computer, electronic engine control, which then signals the metering device to supply the correct amount of fuel. While some fuel systems are intricate, others are straightforward. Smaller aircraft often employ a simple gravity-feed fuel system with a tank located overhead, feeding a basic float-type carburetor. However, in multi-engine aircraft, complex systems are a must. These systems allow fuel to be pumped from various tanks to different engines via a cross-feed system. They might even include provisions for transferring fuel between tanks, which is common in larger aircraft. Vapor lock. Preventing vapor lock is essential in fuel system design. This phenomenon, often occurring in older gravity-feed systems, happens when fuel changes to vapor prematurely, forming pockets that hinder the flow. Vapor lock can arise from pressure changes, high temperatures, or excessive turbulence in the fuel. At higher altitudes, lower pressure can cause fuel to boil and form vapor bubbles, potentially leading to vapor lock in the system. Engine heat can also heat up fuel in lines and pumps, intensifying this tendency, especially during rapid climbs on hot days. The fuel retains heat and might boil easily at high altitudes despite the temperature drop outside the aircraft. Fuel turbulence caused by sloshing in tanks or mechanical action in pumps mixes air with fuel, creating vapor pockets at bends or abrupt changes in fuel lines. Severe vapor lock can entirely block fuel flow and stall the engine. Even a small amount of vapor in the inlet line can restrict flow to the engine-driven pump. To minimize vapor lock, fuel lines are kept away from heat sources, sharp bends are avoided, and fuel volatility is controlled during manufacturing. Modern aircraft often incorporate booster pumps that maintain pressure in the lines to the engine-driven pump. This pressure reduces vapor formation and helps disperse any vapor pockets. The boost pump also removes vapor from the fuel, releasing it through tank vents. Vapor eliminators installed ahead of the metering device or within it help prevent any remaining vapor from disrupting the fuel metering action. Basic fuel system. The fuel system in an aircraft encompasses various parts, each with a crucial role. From tanks storing fuel to engine-driven pumps delivering it, the system involves several components working together. Multiple tanks, even in a simple setup, store fuel, their placement determined by the aircraft's design. Lines extend from these tanks to a selector valve controlled from the cockpit to pick the tank supplying fuel to the engine. A boost pump pushes fuel through the selector valve to a primary line strainer, located at the lowest point in the system, filtering out water and contaminants. During startup, the boost pump routes fuel through an engine-driven pump bypass to the metering device. Once the engine-driven pump reaches operational speed, it takes over, delivering fuel to the metering device at the prescribed pressure. The airframe's fuel system begins at the tank and culminates at the engine fuel system, which typically includes engine-driven pumps and fuel metering mechanisms. In aircraft powered by reciprocating engines, this system comprises components from the initial fuel entry point to the moment fuel enters the intake pipe or cylinder. For instance, in a typical reciprocating engine, the engine-driven fuel pump, fuel air control unit, metering device, fuel manifold valve, and fuel discharge nozzles are crucial components. The fuel metering system in current reciprocating engines regulates fuel in a predetermined ratio to airflow, controlled by the carburetor or fuel air control unit. Gas turbine engines have a fuel metering system composed of an engine-driven pump, fuel flow transmitter, fuel control with an electronic engine control, a distribution system or manifold flow divider, and fuel discharge nozzles. Some turboprop engines also include a fuel heater and start control within the engine fuel system. The rate of fuel delivery can vary based on factors like air mass flow, compressor inlet temperature, compressor discharge pressure, compressor RPM, exhaust gas temperature, and combustion chamber pressure.